Millikan oil drop experiment. The Millikan oil drop experiment, which was the first experiment to measure the charge of the electron, compared the electrical force on a small charged oil drop with the force exerted on this drop by gravity. The experiment thus required a knowledge of the weight of the drop. This weight can be obtained by observing the drop falling with a constant terminal velocity when the gravitational force on the drop is balanced by the frictional force due to the viscosity of the surrounding air. The air is at atmospheric pressure so that the mean free path of the air molecules is much smaller than the diameter of the drop. The terminal velocity with which the oil drop falls is inversely proportional to the viscosity of the air. If the temperature of the air increases, does the terminal velocity of the drop increase, decrease, or remain the same? What happens when the atmospheric pressure increases? The viscosity of the air, eta, is given by, according to elementary kinetic theory, 1 over 3 n number density, mean speed per molecule, mass of one molecule times the mean free path. And for the air molecules, it is 1 over 3 n, and for V bar, we're going to substitute our approximation using VRMS. And remember that we have obtained 1 over 2 mv square. The kinetic energy of the molecules is equal to 3 over 2 kT using equipartition theorem. And this tells us that we have, when we take the average value of these two sides, V square bar, this is basically 1/2 mv square bar is equal to 3 over 2 kT according to the equipartition theorem. So this tells us that if we consider V square bar to be approximately equal to V bar square, then we can say that V bar is approximately square root 3 kT over m. So that's what I'm going to substitute here for V bar, 3 kT over m square root. Basically, this is the RMS value of the speed, but we're estimating it to be close enough to the mean speed. This is m times L, and then we have 1 over 3 n square root 3 kT over m and for the mean free path we substitute 1 over square root 2 and sigma, the total scattering cross section. So the n values will cancel, and at this point I'm going to assume that the air molecules act as hard spheres, assuming that the air molecules act as hard spheres, and I'm going to neglect the temperature dependence of the total scattering cross-section sigma, we will see that the viscosity of the air, due to this square root 3 kT over m term here, has a dependence on temperature as T to the power 1/2. And we are given that the terminal velocity of the oil drop is inversely proportional to the viscosity, 1 over eta dependence. So this tells us that the temperature dependence is T to the power minus 1/2. So we can see that if the temperature increases, the viscosity increases, therefore the terminal velocity decreases. So Vt decreases if temperature increases. That's our conclusion. Now, on the other hand, for the pressure, we have, assuming the ideal gas for the air molecules, P bar is equal to number density Boltzmann constant times temperature. We can see that at a constant temperature, the relationship between P bar and N suggests that the viscosity is not a function of the number density or the mean pressure. So the terminal velocity, which is inversely proportional to the viscosity, will remain the same if the mean pressure of the air molecules increases. So the dependence on temperature is suggesting that the terminal velocity decreases if temperature increases. However, it's unaffected by changes in the mean pressure. So we have utilized this information that the terminal velocity with which the oil drop falls is inversely proportional to the viscosity of the air. Now, the viscosity of the air molecules is, according to elementary kinetic theory, 1 over 3 n number density, capital N over V, volume. V bar means speed per molecule, mass of one molecule multiplied by the mean pre-path. And for V bar, we use this approximation using equipartition theorem 1/2 mv square bar is 3 over 2 kT. And therefore, V square bar, which is approximated to be V bar square, this is saying that we are assuming V bar is the same thing as V RMS, approximately. With this approximation, we obtain a square root 3 kT over m for V bar, and for L, obviously I have also here an m, which I have forgotten. For V bar, I substitute square 3 kT over m. I have m here, and for L, I have 1 over square root 2 n sigma. The n's cancel. And therefore, I will see that the viscosity of the air is proportional to T to the 1/2 if I assume that the air molecules are acting as hard spheres and there is no temperature dependence of sigma. So sigma is approximately temperature independent. With that, the viscosity becomes proportional to T to 1/2, and the terminal velocity, which is inversely proportional to the viscosity of the air, is T to minus 1/2, has T to minus 1/2 dependence. So if the temperature increases, viscosity increases as T to 1/2, terminal velocity decreases as T to minus 1/2. The pressure, what happens when the pressure increases? The pressure is using ideal gas law, number density Boltzmann constant times temperature. At a constant temperature, P bar and N are proportional to each other. So since the viscosity is not a function of N, it's also not a function of pressure. So the terminal velocity will remain the same if the mean pressure increases.